Welcome to my video course on engineering FRMCs. Today, we're diving right into the future railway mobile communication system. We're going to look at exactly how we engineer this thing to handle the incredibly demanding zero margin for error connectivity needs of modern digital railways. Here's a quick look at our roadmap for today. We'll cover the connectivity challenge, multi-access design, executing intra-RAT handovers, integrating public networks, configuring policy rule sets, and finally, zero downtime automation. Let's just jump right in. Starting off with Section 1, the FRMCS Connectivity Challenge. So, we all know that systems like the European Train Control System, or ETCS, demand absolutely strict latency and rock-solid packet reliability. I mean, we're talking about controlling massive trains moving at incredibly high speeds, right? Service continuity simply cannot drop when a train moves between cells. In the old days, handing over meant tearing down and establishing a completely new connection. But today, the demand is strictly zero service interruption. It's a huge challenge. Which brings us to Section 2, multi-access and multipath design. To solve this massive connectivity vulnerability, we rely heavily on multi-access and multipath capabilities. This essentially allows our onboard mobile gateway to use multiple radios simultaneously. It's kind of like a dual-engine train. If one track completely fails, the other one just seamlessly takes the load. Since the FRMC's framework is entirely radio access technology agnostic, we can use a 5G core to coordinate these multiple technologies. By running multiple user equipment devices, or UEs, in parallel, we create this robust, overlapping web of connectivity that basically eliminates single-link vulnerabilities altogether. Moving on to Section 3, executing intra-RAT handovers. Let's look at how an intra-RAT handover actually happens in the real world without dropping a single ETCS packet. If you look at the architecture, you'll notice how the intermediate user plane function, or IUPF, alters the data path right in the middle of a session. As the train physically moves across different cell towers, the connection to the application server isn't broken at all. The IUPF acts as this dynamic bridge, maintaining a single, continuous IP connection while the physical radio link on the ground changes hands. And this handover process is highly methodical. As a train approaches a network border, a network transition trigger, or NTT, actually initiates the setup of a transport path in the target domain ahead of time. Because this path is proactively established, the transport tunnel is already there, just waiting to carry mission-critical signaling by the time the train physically crosses over. The mobile gateway handles the negotiations, and traffic is steered securely and seamlessly right into the new domain. Next up is Section 4. Integrating public mobile networks. Now, relying strictly on dedicated railway-owned infrastructure, or RMR, isn't always feasible, right? That's exactly why we integrate public mobile networks into the mix. By intelligently roaming onto a public mobile network operator, or PMNO, the gateway can actively split traffic or fail over instantly if needed. This gives the train a totally critical fallback layer and some much-needed extra capacity to ensure resilience. The crucial takeaway here is that the onboard mobile gateway uses network address translation, or NAT, to hide all this complex external switching. It makes the transition completely invisible to the train's internal ETCS network. Imagine you're a device inside the train. You honestly don't care if the data is coming from a dedicated railway cell tower, a public 5G network, or even a station Wi-Fi depot. The mobile gateway manages the varying link quality automatically, translates those addresses via NAT, and just feeds a steady, reliable stream of data straight to the train's internal local area network. Let's transition to Section 5, configuring policy rule sets. So, you might be wondering, how exactly does the system automatically decide when to switch or split traffic across RMR and public networks without dropping those critical packets? Well, the answer lies deep within the policy and charging control framework. It executes split-second routing decisions based on very strict, predefined parameters. When a train moves, the network needs to know instantly which application gets priority, which radio link to use, and exactly how to steer that traffic. Let's break down the flow of command. The policy and charging function, or PCF, is essentially the brain defining the unified policy. When a mission-critical application needs a specific quality of service, it provides dynamic input to the PCF. The PCF takes that, formulates strict routing rules, and pushes those instructions down to the Session Management Function, or SMF. The SMF then commands the user plane function to detect packets and enforce those rules flawlessly. It's an incredibly precise, automated chain of command. And when it comes to prioritizing traffic, the number 69 is absolutely crucial.
In the 5G system, this specific Quality of Service Identifier, or 5QI, is assigned exclusively to mission-critical, delay-sensitive signaling. Whether the train is cruising on its dedicated armor network or roaming on a public PMNO, tagging data with 5QI69 ensures the transport bearer prioritizes the train's control traffic over absolutely everything else on the network. No exceptions.
Finally, we arrive at Section 6, Zero Downtime Rail Automation. Let's pull back and see how all of this works together. If you look at the architecture, notice how the PDU session anchor, the PSUPF, stays completely locked in place. As the train physically moves, changing cell towers and engaging different intermediate UPFs, that anchor point to the application server doesn't flinch. This is the ultimate execution of those policy rule sets we just talked about. It secures a persistent IP session so that automated commands never ever experience a hiccup. The real-world result of all this rigorous engineering is that highly automated trains can navigate wildly varying network conditions and cross geographic borders with absolute zero downtime. By integrating this mission-critical framework right on top of a 5G core, FRMCS achieves true multipath coordination. The system automatically reacts to network changes based on those strict service policies, triggering seamless recovery actions without the train's operating system ever noticing a disruption. It's pretty amazing.
So, as we push further toward fully autonomous driving in the rail sector, it really makes you wonder, can these predictive multipath algorithms eventually make the very concept of a network dead zone obsolete? It's a massive question, and to find out, thanks, we can see in next video.